This is Physics2212 Lab2, Magnetic Field of a Bar Magnet. Introduction. In this lab, we will be looking at the magnetic field that is created due to a bar magnet. This bar magnet is a magnetic dipole, and we will look at the effects of this dipole on a magnometer, a phone. Through experimental and computational methods, we can develop a relationship between the magnetic field and the distance between the magnet and our magnometer. Through the experimental methods, we will perform multiple trials of placing the magnet in close proximity of the phone and measuring the readings. The computational model will make use of the Biot-Savart law to determine the theoretical magnetic fields for any distance from the bar magnet. Fundamental physics principles include the following: the electric field of a magnetic dipole for a bar magnet, the Biot-Savart law, the magnetic field of a dipole, and the magnetic field of a dipole off axis. As we can see here on the right is a picture of a bar magnet and the dipole it creates, with the flow of a magnetic field going from the south pole to the north pole. For a preview of the results, we have the observed n value as negative 2.6595, which is the value of mu in the equations. The observed 45-degree magnetic field is negative 8.63 times 10 to the negative 6th for the x component, and negative 1.397 times 10 to the negative 5th for the y component. The predicted 45-degree magnetic field from the computational model is 6.85 times 10 to the negative 6th for the x component and 2.05 times 10 to the negative 5 for the y component. Experimental portion of this lab, I used a simple bar magnet, my phone as a magnometer, and a ruler to take measurements. The first step of this lab was aligning my phone with the north pole of the Earth, which would zero out the Bx value of my magnometer. After this step, I slowly moved my phone up and down along this line to find where the Bx was largest and where the By was smallest, which showed the vertical locations of the magnetometer chip in my phone. I repeated this step with the phone turned counterclockwise 90 degrees, now looking for the largest By and smallest Bx to find the horizontal place of the chip. I now had the exact location of the magnetometer in my phone and could begin taking B field measurements from the bar magnet. The initial conditions provided in this experiment were that the only forces acting on this magnetometer were the bar magnet and the magnetic field of the Earth, the system being our phone, and the surroundings being Earth's field and the bar magnet. The next step was to place the magnet a certain distance away and record when the Bx reading is 20 microteslas. We do this trial 3 times and then average it to find the average reading, and then repeat this for the values of 70, 120, 170, and 220 microteslas. We then record these values in the Excel spreadsheet. When we then plot these results on a graph of natural log of Bx versus natural log of R, we were able to find the value of n, mu, as the slope of the line. By taking the natural log of both sides of the first equation, we can find that n is the slope of line in the plot. We can see here the first equation for the magnitude of the magnetic field of a bar magnet. Taking the natural log of both sides gives us this. For the last part of our experimental model, we will find the 45 degrees off-axis B field. We start by finding the perp distance where the net field is 100 microteslas, then we move the phone this distance directly upward. After we do this 3 times, we find an average net field, which we will compare with our computational model. What is the computational model used in GlowScript? As we can see here, these lines of code are used to create the magnet figure. Here is the function we use to find the magnetic field due to the bar magnet. And here are the observation locations for the various places, with 2 of them being on axis and 4 of them being on the perp axis. Here we can see we begin finding the magnetic field and putting the arrows in the figure for the on axis. Over here, we have the same thing done for the perp axis. I didn't show it here, but we repeat this step 3 more times for each perp axis location. Lastly, we have the 45-degree off axis code shown here to find that magnetic field arrow displayed. This is what we get, with the cyan arrows showing the perp axis and the orange arrows showing the on axis. Over here, the magenta arrow shows the 45 degrees off axis, and we can see that it's much smaller in magnitude. When we compare the results, we see that they're quite similar, but slightly different. As we can see, the magnitudes of the 2 different values are close in value, but the signs of these are different. A possible explanation for this could be the magnetic dipole moment facing opposite directions between the experiment and the model. As for the cause of error for the errors in magnitude, there are multiple things. Incorrect calculated location of the magnetometer chip could have caused this, human errors in measurement, or other possible magnetic fields interfering between the Earth and the bar magnet. First question to ask, what if we were to instead line up our meter stick with the magnetic north, we place it at some intermediate angle? If we were to do this, we would notice that the magnetic field due to the Earth would interfere with the bar magnet's field, resulting in different values from our computational model. For the second question, if we were to redo the experiment and instead line up two identical magnets end to end and repeat the steps, if we were to do this, the magnetic fields would be approximately doubled in the same direction, as the two dipoles would be in the same direction.